Yes. Okay. I'm Leonie from Catalin, the chair of Sichen. This year we have four presentations, and we should bring have 25 minutes. Now let's begin the first presentation. NDN-based data distribution for large-scale data intensive several times. Okay. Let's start with the video.
Welcome to the talk for paper titled N-DISE, NDN-based data distribution for large-scale data-intensive science experiments. My name is Edmund from Northeastern University, USA. So the authors, we have a big collaboration for this paper. So the paper's authors are Yuanhao Wu, Volkan Mutlu, Yuozhou Liu, and myself from Northeastern, Ran Liu from Google, who was previously with Northeastern, Catalin, Iordache, Justice Balkus, Harvey, Newman, Raimondas, Sirvinskas from Caltech, Michael Lo, Sichen Song, Jason Cong, and Lhc Zhang from UCLA, Sankalpa, Timilsina, Susmit, Shannigrahi from Tennessee Tech, Chengyu Fan from Pure Storage. He was previously with Colorado State. David Pesavento, Jun Shaoxi, Lutfi, Men Mohammed from NIST. And this has been a great collaboration between these among these institutions. So the topic here is data-intensive science, of which there are many examples. The most prominent and probably the one we've worked with the most is the Large Hadron Collider high energy physics experiment, but it extends to other fields such as astrophysics, the Large Synoptic Survey Telescope, LSST, the Square Kilometer Array, SKA, and genomics, which we will also be involved with in this project. So the N-DISE project, which stands for NDN for Data Intensive Science Experiments, is supported under a grant from the US NSF starting in 2020. And as I mentioned, the team consists of Northeastern, where I'm leading the effort, Caltech, where Harvey Newman, who is a physicist in the physics department in Caltech and who has been involved with the high energy physics networking project for many years. Lhc Zhang and Jason Cong from UCLA, who are leaders in the NDN project, and Susmit Shannigrahi from Tennessee Tech, who has worked with other science projects such as climate and genomics. And we have done this in collaboration with LHC project, NIST, and the genomics collaborators with support from many valuable colleagues from Internet 2, ESNet, CNIC, Starlight, who have really helped us put together our network on the wide area network testbed. So what are the challenges? Actually, a lot of the data intensive science fields share these challenges. For instance, like Large Hadron Collider high energy physics program manages 900 petabytes at more than 170 sites. And the network traffic in LHC has exceeded 1.6 exabytes in 2019 and will still grow 10 times due to the high luminosity LHC experiment starting in 2027. So they will be having a big data challenge coming up. And based on the resources that are currently available, actually that won't be sufficient to cover these data needs. And this seems to be true across the board in many different data-intensive science fields, including human genome and Earth biogenome projects. In all of these fields, more efficient data access and distribution methods are required. Our approach in this project is to design and implement highly efficient and field-tested data-centric data distribution, caching, access, analysis system for LHC, high energy physics network, and many other major science programs. So we are approaching this problem from an information-centric point of view, specifically using NDN protocols and algorithms and architecture. So just to give you a sense of where the data growth in these data-intensive field science fields look like, the data growth in CMS, which is one of the two largest experiments within the LHC high energy physics, if we look at the total disk requirement, total data requirement as a function of the year, we see that there's going to be a huge increase around the year of 2025, 2026, essentially when high luminosity experiments will be starting. And we see that on the dashed line is basically the increase due to the 10 to 15% annual resource increase, which is available to the project. And we can see that there's a big gap that has to be closed. And this is from the High Energy Physics Network Requirements Review Final Report from ESNet in 2020. And really the only way we can close this gap is short of major investments in resources, which is not likely. We need to have a large effort devoted to fundamentally different and fundamentally advances in research and development. And this is what this project is really about, closing this gap. Let me talk about the major contributions of this project. This project will produce the first high-performance NDN-based integrated data delivery system for large scale data-intensive science applications. It has developed an NDN naming scheme for CMS data, and this consists of a name mapping associating data objects used by workflows with data units used by network requests. We've found that such a mapping is necessary. We've developed consumer and producer applications interfacing with multi-threaded high-throughput NDN-DPDK forwarder, which was developed by NIST, and this is made possible by development of the NDNC library. We have integrated the VIP joint caching and forwarding algorithm, which was previously developed at Northeastern, with the NDN-DPDK forwarder and the NDNC-based consumer and producer. We've established a high bandwidth long-range WAN testbed with nodes at Northeastern, Caltech, UCLA, Tennessee Tech, and Starlight in Chicago. With the support of Internet 2, ESNet, CNIC, we have provisioned dedicated VLANs, which allows direct experiment with NDN protocols and algorithms at layer 2. And finally, we have done extensive testing on this WAN testbed using LHC data files showing that the deployed system achieves a maximum throughput of 31 gigabits per second. And while the VIP joint caching and forwarding algorithm simultaneously increases throughput and decreases delay. And there's been related work in the application of ICN and protocols to science programs. I would just mention that the first two there have to do with more preliminary work from our team in the area of high energy physics. And the next one, the third one, is in the area of genomics, and the last two are in the area of climate. We're going back a couple of years. All right, but the distinguishing aspect of this paper will be the much more advanced and high performance nature of the platform and the algorithms and the implementation. And I think it's fair to say that this has been the most high performance, the largest scale implementation of a ICN based data delivery system for large science programs thus far. All right. First thing I want to talk about in the project is the naming of LHC data. In LHC, there are Large Hadron Collider experiment, there are events, which are units for logging physics events, essentially collisions observed in Large Hadron Collider, which is sitting in CERN in Geneva. And files are sort of a fundamental unit of data. Each file contains around 10 to the 5 to 10 to the 6 events, and they are on the order of several gigabytes. And each file is given a name in CMS of the kind that you see here. And actually, these names are easily converted to a name in NDN by removing certain delimiters and by rearranging. So at the level of the file, it is easy to convert names from CMS to a name in NDN quite naturally. Now, next layer up, so within each of these granularities, such as the file, the name is in fact hierarchical. But when you go one level up in the CMS hierarchy, in the CMS file data organization, you get the data block, which each block contains several or tens of files and constituting several to hundreds of gigabytes. And the name here, there's also a name within the data block level, but it looks different. It does not share the same prefix as the name in the file, which is something that we have had to deal with. When you go one more level up, you have the data set, which contains several or tens of data blocks and constituting several terabytes. And this again has a different structure than the file that I mentioned earlier. So even though at each level you have a hierarchical name, between these different levels, they do not. So content names at each granularity levels are hierarchical. Names can be converted to NDN names at each granularity, but blocks and dataset names do not share the same prefix with the file name. So the issue here then is that CMS workflows use data blocks while the network requests use files, and therefore we have had to build a name mapping hash table at each forwarder, allowing caching and forwarding algorithms to operate at data block level while users request data at the file level. There is a certain mapping that has to be developed in order to mediate between the names at these two different levels. Now, this name mapping table need not change frequently due to the relatively static CMS data structure, and they can be obtained and updated through the control plane. Next, we look at data flows in the LHC network. We analyzed logs of CMS workflow from March 2019 to determine the granularity that we need for caching. And when we looked at the request frequency for files, they were relatively flat. However, when we looked at request frequency for data blocks, we saw a sharper decay. In particular, at Caltech, roughly 6,000 data blocks with unique names were requested, but the most requested 400 data blocks covered roughly 80% of all the requests. And so in this, because of this, in the caching algorithm and forwarding algorithm, which we will discuss, we will maintain control state only over the most popular 400 data blocks. So here you see the data block index on the x-axis and the percentage of requests covered by the data blocks here, and you see a sharp increase there. We also observed data blocks are mostly less than 10 gigabytes, and therefore a 10 terabyte cache can roughly cover 80% of all the requests by caching small data blocks. You see the size distribution of the data blocks. Most of them are less than 10 gigabytes. All right. The next component of our system is the NDNC consumer and producer. So the consumer is basically a client submitting NDN interest packets. The producer is a server with access to file system publishing NDN data packets. We designed a consumer producer applications to communicate with a high-performance NDN DPDK forwarder developed by NIST. So in order to have high performance in our system, one of the biggest things we did was to integrate our components with the NDN DPDK forwarder developed by NIST, which has a multi-threaded structure and which has demonstrated high throughput. And this was one of the biggest integration tasks that we had. This deployment, these consumer and producer applications were deployed using Docker containers. In order to develop these applications, we also developed a lightweight NDNC C++ library, bridging the NDNCXX library with the NDN DPDK forwarder. And this can be found on GitHub. And I'll just mention that this was primarily developed by Catalin Iordache at Caltech, who has made great contributions in this respect. And some properties of this NDNC library is that it offers PIT token support, which is required for interoperability with NDN-DPDK. It has a MEMF face to transmit, receive bursts of packets at a time. It can encode and decode layer 2, layer 3 NDN packets. It does interest pipelining via either a fixed window or a congestion-aware AIMD algorithm. It uses a GraphQL client to configure local forwarders by creating, deleting faces, registering prefixes. This is the essential architecture of the N-DISE deployment here. As you can see, we have the on the left-hand side is where the consumer is sitting, and it can be interfaced with the existing CMS system through an extra D plugin, which we're developing. And then it goes through high performance NDN set of functions through the MEMF interfaces with the NDN-DPDK forwarder, which is implemented in a Docker container. Then it goes to the through the NIC to the NDN network, which is assumed to be a high capacity network here with the NDN-DPDK forwarder here on the consumer side. And the producer side, the producer side, we have a similar kind of setup, and where this producer is able to get files from using calls from on the producer side. All right. The next component of this system has to do with caching and forwarding. And here we're leveraging the VIP joint caching forwarding algorithm, which was developed back by the Northeastern group back in 2014. It was actually published at ICN conference 2014. The reason we do that is of course, again, for performance reasons. VIP joint caching forwarding has very good delay in terms of throughput delay, cache hit ratio performance. It has some of the leading performance there. Now, the idea of the VIP algorithm is to measure demand for data objects in the network by virtual interest packet or VIP counts. Each node will maintain a VIP counter for each data object in the virtual control plane, and periodically it will communicate these counters with neighbors and update the counters. The evolution of the counters follows controlled queuing dynamics. VIP counts are incremented at entry nodes of the request for a data object and decremented at a rate proportional to the readout rate of the cache node at a caching node, and at 0 at the source of the data object. So we can view the VIP counts as a kind of a potential. The VIPs for data objects follow a gradient from a high potential entry points of these requests to low potential caching and source nodes. Forwarding in the virtual plane basically applies the back pressure algorithm to VIP counts and allocate VIP transmissions to minimize the VIP count differences on each link. Caching in the virtual plane will cache objects with the highest VIP counts subject to cache capacities. And in the actual plane, we will observe the flow of VIPs in the virtual plane and use this to make forwarding caching decisions for actual interest in data packets. So for more details on the VIP algorithm, you can refer to the paper that we had in 2014 in the ICN paper. So here's a diagram of the VIP implementation here, where we integrated the VIP forwarding caching algorithm with the NDN-DPDK forwarder, which we're calling the VIP NDN-DPDK. And here you see that we have the virtual plane here, which is doing the forwarding and caching in the virtual plane. And this then, by observing the pattern in the virtual plane, it informs what we're going to do in the actual plane here, which is actually handling the forwarding of the data and the caching of the data packets. And there will be exchange of information of every particular node with its neighbors here. All right. Now, some specifics on the VIP NDN-DPDK implementation. The VIP control state is maintained for a set of registered data objects, each consisting of a set of chunks. In the CMS application, the registered data objects are chosen to be the most frequently requested data blocks. So for instance, this is the 400 data blocks out of the 6,000 which was most frequently requested. The names of the registered data objects are stored in a cache table called the name map table, which also stores the mapping from the chunk names, namely the file chunk names, and the corresponding data object names, which are the data block names. Remember, we had this difference in the names at these two different levels, which has to be tracked. The VIP algorithm is applied only to the registered data objects. The other data objects which are not cached, so the less popular ones are not cached, and they're forwarded using default forwarding strategy of the NDN-DPDK forwarder. All right, so in the virtual plane, in VIP NDN-DPDK, each node asynchronously exchanges these NDN-based VIP control packets, which contains VIP counts and transmission rates with its neighbors every T seconds. Nodes then update their VIP-related statistics. The cache score for data object K in node N is implemented as an exponentially weighted cumulative received VIPs for data object K at node N. In the actual plane, we forward interest packets for data object K at node N to neighboring node M with the maximum exponentially weighted cumulative VIP sending rate. Okay, so this is something which is based on the VIP flow in the virtual plane. And in the actual plane, the VIP algorithm requires all chunks of the data object to be forwarded, cached, and evicted from the cache together. And there are ways to ensure that. And then the caching policy maximizes the total cache score of the cached data objects. So that's a summary of what VIP and the NDN-DPDK does. Now to the WAN testbed. We have put together a testbed consisting of high capacity links among Northeastern, which is actually placed at the MGHPCC site with Caltech, UCLA, Tennessee Tech, and Starlight in Chicago. So in Caltech and Starlight, there are actually two servers. All the servers are connected by tagged VLANs with support from Scenic, Internet 2, and other server sites. So this requires a lot of collaboration from many entities, and we're very thankful for their support over the last many years, in fact, to put this together. In terms of the equipment we're using high-end Intel Xeon or AMD EPYC CPUs. Memories of these servers range from 96 gigabytes up to 512 gigabytes. We use large pools of both HDD and NVMe SSD storage. We used Mellanox ConnectX series NICs supporting 10 to 100 gigabit Ethernet. And so this is a very high performance test bed on a wide area network, in fact, transcontinental across the country. And you can see the different colors of the links on this picture indicate the capacity of the link as the theoretical limit. Okay, so ranging from 10 gigabits per second to 100 gigabits per second. And the times there are the round trip delay on these theoretical round trip delay on these links. So the first test that we did was a throughput test. So we measured the average throughput from Caltech 1 on this diagram, Caltech 1 to Starlight 1. Now this is a 100 gigabit link theoretical capacity, okay, but when we actually measure the IP throughput over this path using iPerf3, this was measured at 31.8 gigabits per second because, of course, there are other things going on the link besides our project. We measured the throughput, and here is the throughput from Caltech 1 to Starlight 1. The x-axis indicates when you see, for instance, 6C3F, that means that we're using 6 consumers and 3 forwarding threads, okay? So we also have this NC versus non-NC. NC means the result with a no cache test so that you can do caching either at the producer Starlight 1 or no caching. So if you don't have NC, then there's no caching. And then there is caching, in fact, at the producer. So you can see that we have an increase in throughput as we use more consumers and we use more forwarding threads. Actually, when we get to 12 consumers and 4 forwarding threads, then we start not getting much improvement. This is average throughput over 30 minutes, okay? And the peak throughput actually that was achieved was 31.14 gigabits per second using the 12 consumers and 4 forwarding threads. This is very close to the capacity, the throughput, which is measured by IPERV3. And you see, and so the figures we have here are the average throughput, but the peak throughput is very close to that measured by IPERV3. So the throughput that we obtained on this system, and remember, this is using NDN forwarding, right? So this is actually very high performance for an NDN system, and probably the fastest that we've gotten over the past few years. So N-DISE is a high performance system. Now, the next thing we're going to evaluate is the caching forwarding performance, and we're going to look at two different topologies here. The first one is a service network topology with 2 consumers and 2 forwarders and a producer here. This second one is a multi-path topology with 2 consumers here in Northeastern, Tennessee Tech, and forwarder here in UCLA and Tennessee Tech. So here we have 2 different paths we could take, and here we have only 1 path. So here primarily we're going to test caching. Here we're going to do joint forwarding and caching. So what is the experimental setting? The request node will run 1 NDNC consumer per request node with a fixed window of 881.92 packets. We have a 2-second transmission timeout. These are all parameters which has been tuned for optimal performance. We have request 30 registered data objects, each of 4 gigabytes according to ZIF1 distribution. This is distribution which is estimated from empirical data we've collected from LHC. At the forwarder, we have each forwarder has 20 gigabyte of cache space, which is tantamount to 5 data objects. And we test 3 kinds of caching policies: no caching, the adaptive replacement cache ARC, which is an improved version of LRU, which is developed by NIST, and VIP, which is the joint forwarding caching policy developed by Northeastern. And we use just 3-second time slot. And we can see here are the results. We have plotted the throughput in gigabits per second versus delay in milliseconds. And the delay is averaged over all packets at the consumer, all requests at the consumers, and the packet delay is measured from the time that the request is submitted until the fulfillment time, averaged over all packets. And we can see here that we have 3 sets of things. The square quantities are the delay versus throughput under no cache VIP and ARC at the Starlight. Remember, we have 2 consumers here, the Starlight consumer, and we have a similar set of things for UCLA, which is the other consumer, the triangle. And then we add over both consumers, we have the final numbers here, which is the overall. And you can see this is very clear that the VIP numbers are actually in this orange here. ARC is in blue, no cache is in red. You can see that VIP is simultaneously increasing the throughput and decreasing delay. Okay, so this is this plot shows it very clearly. It is able to improve significantly the performance in both dimensions. This is in the first service topology. We will observe that in the service topology, the first forwarder, which is at Northeastern MGHPCC, always caches the 5 most popular files. Okay, so this is exactly what you would expect, because here, right, you would expect to cache the most popular ones, whereas the Tennessee Tech forwarder always caches the next most popular ones, ranking from 5 to 11. So this is exactly what we would expect, and VIP is doing exactly what it should do. So this VIP NDN DPDK simultaneously achieves higher throughput and lower delay per packet at both the Starlight and UCLA servers. The second experimental setting is the multipath topology. And here we have 2 consumers, Northeastern and Tennessee Tech here, and forwarders at UCLA and Tennessee Tech. And you see here, the interesting thing is that we have 2 paths that we could go in, and you also have to figure out how to share the resources of the consumer and forwarder at Tennessee Tech. So here, the interesting thing is that we have to do joint caching and forwarding. And now you would expect perhaps a greater benefit from running VIP, which is a joint kind of strategy. Here we have a 1-minute time slot and VIP amplification factor of 2. Here the parameters are chosen to get a bit more buildup in the VIP counts. And because in the multipath topology, the interests are kind of diffused, and therefore you need more time to build it up. And the VIP amplification factor also allows you to do that. The other parameters are the same as in the service network. We compare three policies: the round robin forwarding plus ARC, fast route forwarding plus ARC, and the VIP algorithm. Now, round robin basically means that you're going to choose the forwarding path in a round robin fashion plus ARC. The fast forward basically means that among the different paths you have, you simply measure the one with the fastest response and you choose that one for a while. And then after a while, you measure again and you adjust as needed. Okay. So again, looking at these throughput versus delay numbers. Let's just look at the overall numbers here between round robin plus ARC, fast route ARC is in orange, and VIP is in red. And again, you see that VIP is able to improve significantly in both throughput and delay in the overall sense. And in fact, also it does the best if you look at the individual consumers also. So again, this is a confirmation of VIP's performance. And also when we look at cache hit ratios, which is if you take all the cache hits divided by all the requests, once again, VIP comes out to be the top, significantly better than round robin plus ARC and fast route plus ARC. All right, so these are the experimental results which we've obtained. And this is actually, because we have to obtain an overall a WAN test bed, this actually required a lot of time and a lot of engineering. And so there are a lot of lessons which we learned from this process, which I think might be valuable for the community. One is that there are challenges in mapping application names to NDN names. So here we needed to develop a mapping to associate data objects used by workflows, as in blocks of CMS data, with data units used in network requests, which are, in this case, files of CMS data, as we mentioned. We have to do this mapping. And this is very important for practical system. Secondly, we needed to decouple control plane information from forwarding threads. So we observed that transmission and parsing of control packets may interrupt operations of forwarding threads, and it is better to allocate dedicated threads where control information is generated and parsed. Third, there is the impact of middle boxes on NDN-based protocols. Experiments revealed many disruptive effects of intermediary network devices on expected behavior of NDN protocols. For instance, NDN packets were often corrupted in transit. So to deal with this, we used virtual extensible LAN encapsulation protocols, VXLAN, to tunnel NDN packets over UDP/IP. This hides NDN packets from middle boxes and prevents corruption, but also leads to reduced throughput. This is something that other projects have also encountered and very notable. Also, system-dependent configuration and tuning. This is something we spend a lot of time on. Yeah, even though we used Docker containers to package the forwarder, the consumer, and producer, which improved things quite a bit, but these deployments still inevitably interact with diverse server equipment, operating systems, network configurations, and we still needed to spend substantial manual effort for configuring drivers, ensuring proper usage, integrating software stacks into the workflows. And this entailed a large amount of trial and error experience, unfortunately, but this kind of project definitely requires that. To conclude, we developed and prototyped N-DISE, the first high-performance NDN-based integrated data delivery system for some of the world's largest data and network-intensive science programs. This is a project that we have worked on for actually going back 5 years or so to a previous project called Sandy. And so we're happy to see some significant, still initial results, but very promising and significant results. We've combined NDN naming scheme, a new consumer and producer application, jointly optimal caching forwarding algorithms. We've integrated all of these components with high performance NDN DPDK forwarder. We achieved leading throughput of around 31 gigabits per second and delay performance in real world WAN settings. So that's all very good. There is still a lot of work to do in spite of these results. We want to integrate NDN with mainstream NDISE, the system with the mainstream LHC data distribution systems. Primarily, this will be done through the plugin with the XRUD system that LHC uses. We are interested in multi-threaded forwarding and hierarchical caching with VIPs. It's something we're actively working on, making the forwarding and the caching multi-threaded to integrate with the NDN DPDK forwarder. And we want to do hierarchical caching, which is able to exploit various kinds of storage, including SSDs, hard disks, and NVMe and technology, be able to handle caching, not just with DRAM. We want to do congestion control based on network feedback. We would like to use FPGA acceleration to accelerate some of the table lookups that we have in the forwarding and caching operations. We would like to integrate with genomics workflows. We are looking at data integrity and provenance using NDN protocols. This is something that's very important for scientific experiments. We will be integrating with Sense, which is a platform which gives some service guarantees and SDN control over the links and paths, which would be very helpful for the NDISE project. Now, I said this future work. In fact, a lot of these are already being explored and well underway. So in another year or so, we expect to report on significant results in these aspects. So thank you very much for joining the talk.
It's really very interesting itself. So some mentions in the snap book about congestion control and some conditions for the NDN design. But however, there's no authors here. You can ask a question. Oh, they also online. Okay. Also, can you answer the question from Dave? Why from I repeated the question. Do you envision congestion problems on this network? If not, why not? If so, what approach for the congestion control are you doing? Is also here. Okay, because we have already. Unmute. Could you unmute this? Could you need to unmute this? Yes. You need to unmute. Sorry, we have no time. You can ask, you answer in the chat. I think that there are two questions in the chat. You can answer in the chat. We have to move to the second presenter. Because we use the video, already see the presentation time, 25 minutes. Okay, we need to move to the second presenter. The second paper title is building a secure and beautiful data sharing infrastructure for NDN. The presenter is Sankalpa from N-DISE. Okay.
It's Japanese. Okay.
Video.
Yes. Okay.
No, I want Google slide.
Hmm?
Can I do it? No, I will do this.
Okay.
Can I get a browser?
Browser.
Oh, can you stop the sharing screen for a while?
Okay. Okay. Sorry.
Okay.
Okay. Oh, sorry. Sorry. Yeah. Okay.
Maybe I would use my. Okay.
Yes.
Okay. Can you hear me? Fine. Okay. Hello, everyone. I'm Saurabh. I'm from University of Memphis. I'm going to be presenting our work on building a secure ML data sharing infrastructure over NDN. So wearable devices are growing very exponentially. They're extensively used for M health and willingness and all the stuff. And they're even expected to grow even more in the future. The data produced by these devices can do a lot of stuff. Diagnostic, therapeutics, real-time medical intervention, and many more stuff. But there are significant challenges in sharing the M health data and to achieve those wonders that I've shown in the previous slide. The characteristics of the data, if you look at, they're highly diverse in nature. Several devices, sensors, and are used to collect those data. Many sensors are embedded in the same device. And apart from that, there are privacy and legal concerns. So data contains personal information. Usually they are overseen by IRBs for research and use, and they are also protected by federal laws. So when we think about taking into consideration these characteristics and the privacy legal concern, securely and by maintaining a privacy, sharing the data becomes non-trivial. The challenges also exist within the system. So we specifically look at this, one of these system, MD2K, their mHealth research cyber infrastructure. So MD2K is an NIH center of excellence. They do data sensing, collect a huge amount of data, and then try to figure out the knowledge out of those. And when we look at their system, the access control were very limited. This data were protected by username password. In all the cases, data were manually identified. The authorization of the data were manually identified, and then these data were encrypted manually, and then put in the device and then share them to the users by mailing, which is a very slow process, also subject to human error and everything. And another thing that we found was there was no any real-time data delivery. For so many medical intervention, the ML system needs real-time data delivery. There are also other limitations existed in some of the state of how the system. We did some comparisons based on these key mHealth matrices, and then we found that most of this state of the system did not have contextual access control policy, contextual access control. So I'm going to be talking about a little about this in the next slide. We also look at the whether they support the high frequency data or not. It was also very limitedly supported. And also real-time data distribution was also partially supported in some of the system. So looking at all these limitations and data sharing challenges, we kind of categorize our goal for this project as following. We want to support a real-time data delivery and also want to support fine-grained contextual access control. So talking about that contextual access control, Alice, she might want to share her health data with her doctor when she's eating but not at home. This is a kind of a location-based context. Similarly, she might want to share her physical activity data with a gym instructor when it was the data was collected at gym and at some particular after some time. So that includes a time and location-based access control. So this kind of access control is called contextual access control. So we want to support that. So to achieve this goal, what we need? First thing, we need a better naming scheme of how the data are named and the streams are named that is produced by the participants, so that we can enforce access control policies based on those names. We need a better trust model so that the parties involving in the system can trust each other to share data and to access the data. And we need access control. We need access control policies so that it can tell who and how the data can be accessed. And we need also attribute-based access control, which will provide this contextual access control. And then also finally, we also need a publisher-subscriber system so that real-time data can be sent. Data can be sent in real time. This is the overall picture of how the data flows in our system. You have an mGuard, which the system that we built. Which will process the data from the mHealth repository, encrypt the data, and then inserts the data into the NDN repository. And user with having an appropriate access right can ask for the data, and then the system will verify whether the user is a legitimate user with all those access rights. And based on those verifications, either the system can send the data back or deny the data. So now I'll go into the design of our system. Oh, sorry. Before going to the design of our system, obviously the question comes, why NDN? During all this presentation, we have already seen what benefits we get from the NDN. In the previous presentation also, we saw that. But two of the specific property of NDN that kind of inspired us to use it for this system was large-scale data distribution. We saw that in previous presentation, which is how NDN supports that inherently within the architecture, and also the data-centric security, which these two things are very crucial for mHealth and when sharing data to a large number of audience. So these properties kind of inspired us to use NDN. So going into the design of our system, we need a naming scheme, as I said in the previous slide. So we looked at the legacy naming of the MD2K system, and it was not well structured. The streams that they produced were kind of arbitrarily named. We tried finding the pattern on those names, and then we kind of saw that it was loosely defined in this structure. But after doing a lot of analysis on those names, looking at a lot of streams, we kind of restructured the whole naming system, their naming system, and then converted that naming system into a hierarchical naming system, and that hierarchical naming system into the NDN naming system. So these namings that we designed was based on the semantics and the physical property of the names. For example, you can have an organization, and then that organization can have a lot of studies going on, and a lot of participants can be under the study, and then this participant can have these devices, either phone or other devices. These devices can have sensors, and that sensors can collect the data. So this is a kind of a property and the hierarchy that follows when collecting the data. And this is so intuitive and can be translated to NDN hierarchical naming system pretty easily. So that's why we restructured the whole naming convention. We come up with that was for the data stream names, the stream that is produced. For the application data naming, we need unique data naming for the applications. So it is pretty simply, we attach the timestamp, which is a unique ID in their system. And then we attach that and got the application data naming system, and also we design other namings that is needed for our system. Trust model, as I said before, is very important component of the whole system, because entities need to trust each other. And to establish trust between these entities, we need trust model. So in a high level, we have these entities in our system: access manager, publisher, data requester, and the operator. So this MD2K operator, which has a trust anchor, that is a self-signed public key of the operator, certifies access manager and the publisher. Once they get the right certificate, access manager and publisher can sign their data that they produce. For example, access manager may need to produce some encryption parameters and decryption keys, so it needs to sign that. Similarly, publisher may needs to produce its data. For example, in our case, it's a manifest, so it needs to sign those things. For data requester, it is a little bit different because data requester not necessarily will be from this prefix, like the organization, the mHealth organization. So it can be from outside. So it will obtain the name from whichever organization it is participating from. So for example, it can be from this, a different organization, or from that within that organization too. So for data requester, it needs to obtain the public key cert from trust anchor, which is in our case this MD2K operator. And then once the public key cert is obtained, it will ask for the decryption keys, because every requester has its own policy which defines what data that requester can access. So it needs to obtain the decryption key so that it can get the data and then decrypt it. So access manager will verify the requester's request, and then will check what the policies are for that requester and provide the decryption key. That's how we establish a trust model in our system. The more work on this one was presented yesterday in a poster, so you can take a look at that also. We need a better access control policy. So the access control policy, we have to design a new access control policy. It should be high level enough so that the people in mHealth can understand, and it should also breeze so that we can convert this policy into low level, a bit low level policy which can be processed to achieve a access based on the names. So we came up with this kind of a policy specification or description. By default, we want to allow data access to their owners, because they can access their data, explore the data, and then do a kind of analysis on and evaluate the concerns that they have. For example, if I'm sleeping, don't share my data. That's what the participant can say. So they can do this, explore the privacy concern. And then they can also help in writing more general access control policies for all the users. So the policy structure is pretty simple. It will have a policy ID, a requester names. In this name, it can be if the data is being accessed by a group, it can have a group prefix. If it is accessed by an individual user, then it will have the name of the individual user. And the attribute filter is another section which is also very important, because it will define how the data can be accessed. For example, if you see this here, there are some allowed attributes. For example, the user can access all the data under this stream. It is collected at gym, home, and after some time, but not when the participant was sleeping. So you can achieve this kind of fine-grained contextual access control based on this policy specification. So the next thing, as I said, we need to implement that access control policy into a little bit lower level so that this can be interpreted and applied in NDN context. So we use NAC AVE policy support for that. Again, the goal is to provide the fine-grained access control based on the attributes of the data and the policies. Specifically, we use KPAV, which is key policy attribute-based encryption. More detail on this can be found on the paper, but I will highlight some of the key points here. So NAC-AV will provide us data-centric security, automatic key management, all the keys involved in the system. It does not have to rely on some other external applications. So we have another module, which is a policy parser that will basically convert the policy that I've shown in the previous slide to an AVE policy. And then once it is converted to AVE policy, the requester can access can get the decryption key for its policy. The rationality behind using a KPAV, which is as I said, is a key policy attribute-based encryption. The key of the user associated with the policy. There is another encryption mechanism, which is CPAV, which is a ciphertext policy attribute-based encryption. The few of the features that we were looking at was when the data is produced, there's no idea during the time of production who is going to access this data. Like for example, participants are wearing a watch, collecting a lot of data, but at that time, we don't know who is going to access that data. So we need a encryption mechanism that will allow us to encrypt that data during the time of creation. And it is kind of independent of the policy that will be written in the future. So we wanted that, and that was provided by KPAV. And also, change in policy in the future will not require the re-encryption of the data, which is both kind of a distinction from ciphertext policy attribute-based encryption. One important thing to note is that these content keys are symmetric keys. These symmetric keys are used to encrypt the actual object. So that's why this will help us achieve much faster encryption. And also, if there is any update in the decryption key based on the policy, then it will require the re-encryption of content key only. Yeah, this figure basically shows how the content are encrypted. Like we use the content key, the content are encrypted. These are sent back. These are sent to the consumer. Consumer will use their decryption key to decrypt the content key. And once the content key is decrypted, the content will be decrypted. And the decryption key of a user is based on the access control policy. So that's how you achieve the fine-grained access control. So as I've said, like we need a POPSUP API as well because we want to send the data in the real time as much as possible, as faster as possible when it is published. Our system POPSUP API is built upon NDN sync, which is kind of a transport for NDN, and then it will facilitate for publishing the data and also to the one important thing to note in the POPSUP system is that our security is built inside the system. So the high-level application doesn't need to care about how the security is done. There are some configuration that has to be done while installing the application, and after that, everything is inside in there. So that's one of the feature of our POPSUP application. So this is the overall picture of how it looks like. So publisher application can publish the data. Publisher will basically encrypt this data based on the attributes of the data, which is also supplied by the publisher, and then create some manifest, which I'll talk about in the next slide. And all of these things into the repo, and then in the subscriber side, application will subscribe or unsubscribe some data stream that is interested in. For example, maybe astronomer data or battery data, based on what the consumer is interested in. And then we use sync to exchange the manifest, which is published by the publisher. And once the manifest is received by the subscriber, it will fetch the corresponding data, decrypt it, and send it back to the consumer. So that's how the POPSUP API works. So we use manifest. We had a little bit of problems because we were dealing with like millions and millions of data packets. And then when we try to sign and verify the millions of data packets individually, it's a huge overhead. So we wanted to get rid of that. And additionally, if we have a lot of those data packets, if we publish those individually into the psync, that can also lead to excessive overhead. So we wanted to solve both of these problems, and manifest turns out to be a wonderful solution. So what we do is basically we produce a manifest for a data stream. So that manifest will list all the data names along with the digest. The publisher will sign this manifest and then publish this manifest using a psync, sync. And once the consumer receives this manifest, it will extract the data names, fetch the data names, and they computes the implicit digest, compare the digest. That's it. Once the digest will match, the verification process is done. So you don't have to verify all those individual data packets. And also, additionally, you get this redirection because sync requires sequential naming. The data names are not sequential. And when you do this one level of indirection, you achieve that as well. So both of these problems are solved by manifest. This is overall picture of our system. I don't want to go into the detail of the system. This is how we put these components and the interaction happens here. For more details, you can check out our paper. We have described it pretty well. So we have implemented this in C++. It has a high-level POPSUP API. We use NDN6 library. Did some of the contribution to existing repo because we wanted some of the features. For example, KPAV was not there in NACAV, so we have to implement that. And also did, during our diagnostic, we found a bunch of problems, and then we also contributed to those libraries as well. For the performance evaluation, we use mini-NDN. In the tutorial, we demonstrated that. For our experiments, we compare a few of the experiments that we did was rate experiments and also packet size experiments. So in the RAID experiments, what we did was we used this policy, which basically tells access all stream under some prefix. We publish the data 1 to 8 data points per second, and then this is the result that we found. So normalized delay. So in our system, we have to fetch the manifest, we have to fetch the content key, we have to fetch the data. So there's many retrievals in the system. So that's why we have a lot of these delays. When we see at these delays, normalized delay, we see all of those is kind of increasing along with the data rate. So we found out that as the data rate increases, so some of the manifest propagation and the fetching delay was also increasing. This is still a research for us right now. We're actively investigating that why this happens. But our initial guess was like the sync was kind of a little bit, contributing to that, and also some part of the repo that we use, it was contributing on that. That's what we have discovered, but this is still an open for us. The cryptographic delays almost remain constant because we are not changing the packet size, so that's why it was almost constant. We also checked the packet count, which is maximum major packet count. So in our system, as I showed in the previous slide, we use a lot of retrieval, so there are a lot of packets of different types involved. So we compute the overall packet count, how much you expect and what you get in the system. So our packet count was way less than what you expect, because obviously this is due to NDN, intersegregation, and data caching. So that's why our packet count was very less. Another experiment we did was a packet size experiment. So in this experiment, what we did was we put large number of packets in large number of data points into a single packet, like from 10 to 70, and then we run the same experiments, and we found that normalized delay in this case was almost constant. This also kind of gives you a hint that sync and the retrieval might be causing that more delay in the previous one, because here, if you have a less number of manifests being published, then sync does not get overhead, and also the retrieval is also less. So that's why it kind of remains constant. And then for the cryptographic delays, it increases because we are increasing the packet size, because we are putting more number of data points into a single packet. So that's why they obviously increase. So a few of the lessons learned during this project, building this whole infrastructure, when implementing the data-centric design, it can be sometimes counterintuitive if you try to adapt to what the legacy system is, because we spend months and months trying to adapt to what they are trying to achieve. And then we have to change this whole narratives and then go into the other way of thinking in terms of data-centric design. One of the example was the access control policy that I've shown. Like in the very beginning, early days, we try using some kind of firewall rules kind of things or database query kind of stuff, but it didn't work for us because we wanted to do this contextual access control. And once we moved to the attribute-based design, everything becomes so intuitive and easier. Naming was another thing we have to learn, because it was very haphazardly named previously, so we have to go through all of those and then kind of redesign everything. So this can be also a good lesson for the future. NDN libraries, specifically some of them which we have used, are best when they are for a specific case. But when you start to scale your system, a lot of nodes or the data you start changing those, some of those starts breaking. And integrating those into a single infrastructure is a huge task. That's what we found. So in general, overall, so the key takeaway of this whole project was we built a system to achieve high frequency data transfer with a more fine-grained contextual access control, which are not available in current state of the art out of the system. So that's why I think we moved into the right direction, at least for now. So there are a lot of open issues and future works. Right now we're already exploring some of them. OpenAV, which is kind of an ACAV, which is very reliant on OpenAV, is not actively maintained. We have to find another library or need to implement something ourselves. KPAV, which we have used for encryption in our system, if there are a lot of attributes in access control policies, then the key size will be very big. That might also cause some of the problems, which is still an open scalability issues. End-to-end privacy, one of the important things, because in our system, the participants will generate the data, and this data are shared to the other people. So the participants will not have an idea that how the data is shared. Sorry, who was accessing the data? Rough idea based on the specification. Oh, this guy is accessing the data, but cannot verify it right away. So that's one of the things where we have to actively look into in the future, and revocation mechanism is also something that we have to look, because immediate revocation is not supported right now. Yeah, these are our references. Thank you so much. I'm open for question if we have time.
Thank you. Any question from the audience on side? Yes.
I'll read from the Slack. I think it's always going to be questions in the Slack channel anyway, so so I have sort of 3 related questions. You can decide which ones to answer here, or just tell me to go away. Answer all one. First is, are the manifests encrypted? Are the manifests encrypted, and if so, which keys?
A manifest or not encrypted.
So that means anybody on the network can see all the names in the manifests.
Yes.
Number 2. How much can be learned by looking only at the names and the access patterns? How serious are the privacy implications, even given that the actual data is encrypted? This is a standard name privacy question.
Right. Right, but kind of we think about this sometime. How much we lose from lose privacy just from the names, because names can be the interest uses those names, so that's why interests are always open in the system. Anybody can look at that. So I cannot answer you how much it can, because I don't know how much it can actually cause a privacy issue. But thinking from the very bird's eye view, I think it's very, very less, at least for now. That's what I think.
And then lastly, it seems perfectly like a good design decision to adopt ADE, right? But having adopted ADE, why don't you just adopt attribute-based naming rather than using NDN hierarchical names? Because the right match for an ADA encryption system is actually an attribute-based naming system, not a hierarchical naming system.
I think that's a very good question, which I haven't thought about. But I think we do more than there are other things also involved in the system, like you have to do routing on some specific things, and maybe considering all those stuff. Hierarchical naming will be more beneficial. And also, one important thing with...
I mean, this is sort of all by the wayside of the last 8 years, but there was a pretty practical attribute-based naming system done by Schuler and company way back in 2013, right?
Yeah. Yeah, I mean that's I will take a look on that issue, but I cannot comment a lot on that right now. Hierarchical naming, you can also achieve the access to a certain granular level with hierarchical naming. For example, if you want to provide an access to a certain study, then you can use that particular prefix to provide access to everything underneath that study.
Sure.
So
anything you can do with hierarchical names, you can do with attribute-based names, but the reverse is not true.
Mm-hmm. Yeah. Okay. Thank you for the question. I'll take a look on that.
So, any other question from outside? There is also another question raised in the chat from the. This question is: MPLs seem to be a good example for the information technology application. Would you say it needs information technology network, or would the design look different if it wasn't based on NDN?
Which question was?
The first question. The first question from the.
Oh, okay.
Yeah. He asked whether the design looked different if it wasn't based on NDN.
So some of the things that you want to achieve, as I said, like you know, the distributing the data to a lot of participants is one of the big challenges when you want to do with other architecture. So with NDN, you already have this many-to-many communication or one-to-many communications. So that can be very, very helpful. Yeah, that's one of the benefit, and you have other benefits that you get when it comes with NDN. So I would say that yes, the design may look a bit different, but we also have many things that we achieve with when we sacrifice some of this stuff, going from other architectural design to NDN design. Yes, that's what I think.
Okay.
Yeah.
Thank you. Then last question from page 8. By using KDB, the last one, again from the last line, by using KDB, the encryption has no control over who can access the data, so that the issuer should be fully trusted for giving appropriate keys in this case, since the policies are inside the key. How do you assume it in your security model?
Yes. So while encrypting data, the encryptor has no control over who can access the data. That is true. I mean, it's a kind of a thing. You know, the direction that we chose to go to that path is because the encryptor in the system, we already have a better trust model and everything established in the system. So yes, it inherently assumes that whoever will be writing the policy will not, you know, kind of a trust on that one, the person who will be writing the policy. So that's why we did that. So it's a kind of a decision that we made. Yeah.
Okay, thank you. Just one comment from me.
So yeah.
Maybe you need to express the threats very clearly and then perform the security analysis for the security protocol design. Just one comment. Okay, thank you.
Yeah, thank you.
Is the next here the paper? The next paper title is Intolerant ICN and its application to LoRa.
Can you hear me?
Okay. Okay, hear you.
You can hear me? Okay, well, then let me try to share the screen. Do you see the slides?
Yes.
I'm sorry, I can barely hear you. Could you see my slides and hear me well? Could you maybe give me a sign if you hear me?
Yes,
if you hear me?
No problem. Let's go ahead.
Okay, thanks. Okay. So I assume that you might have introduced me. Thanks for that. And welcome from my side. My name is Peter Kietzmann, and I will present our paper, Delay Tolerant ICN and its application to LoRa. This is joint work with José, Dirk, Thomas, and Matthias. So this is a simplified vision and what we call a regular ICN in this talk. It consists of networked ICN nodes with caches that are typically connected with wired links that expose latencies at the order of tens of milliseconds. But how do we connect the edge to these networks, which might introduce much longer delays? In this talk, we start from the observation that connecting regular networks and edge networks have different understanding. I'm sorry, here was some distraction. So we start from this observation that regular networks and edge networks have a different understanding of round trip times, which affects the timing behavior and state configuration of nodes. In our case, we consider a LoRa-based constrained IoT network at the edge, which introduces delays at the order of 3 orders of magnitude above those of a wired network. But first of all, what is LoRa? LoRa is a wireless long-range technology that transmits data over multiple kilometers with little energy requirements. Thereby, the throughput is heavily limited. LoRa defines the chip spectrum modulation, which is robust against interference, multipass fading, Doppler, etc. So these properties make it an attractive technology for the constrained IoT, where nodes are battery operated and send sensor data sporadically. LoRaWAN is the most popular communication system for LoRa devices and defines a vertically integrated network architecture to upload IoT data to a server-based infrastructure. At the ICN Conference 2020, I have already presented our poster that raised the question whether LoRaWAN is an option for ICN. The short answer is no. In a nutshell, the unreliable uplink communication in LoRaWAN leads to wireless interference, and more severely, centralization around the network server complicates data sharing. To overcome the LoRaWAN limitations, we have proposed and simulated a system redesign in our previous paper. It consists of two. I'm sorry, give me 1 second. So I'm very sorry for that. So far we found out that LoRaWAN is not an option for ICN. So what we did in our previous paper to overcome these LoRaWAN limitations is to propose and simulate the system redesign, which consists of two components. First, an information-centric network layer. We think that ICN has many built-in features that help in dealing with the challenging LoRa domain. Most prominently, obviously, caches reduce wireless link utilization, which facilitates node sleep in the IoT. And second, a new MAC layer. The 802.15.04 DSME MAC handles LoRa-based media access reliably and enables low-power operation. But the round-trip times of 20 to 120 seconds that we found in our simulations still challenge practical ICN forwarders. And this is the starting point for the present paper. Here we aim for a delay-tolerant integration of LoRa edge networks with very long and vastly different round-trip times into a regular and fast ICN network. To achieve this, we provide an OS-level implementation of the DSME MAC on top of the LoRa PHY in the IoT operating system Riot. We introduce new application-agnostic gateway behavior at the edge. These gateways act as layer 3 routers and include ICN caches instead of just bridging to a network server like in LoRaWAN. Additionally, we leverage two recently proposed ICN extensions in our design, namely RISE and reflexive forwarding. And finally, we will provide an experimental analysis on common IoT hardware. We provide comparative evaluations for basic ICN, we call it vanilla ICN in this talk, and the aforementioned extensions. Now, in the remainder of this presentation, I will first dive a bit deeper into the problem space, the role of interest and timeout values, as well as common retransmission procedures. Afterwards, I will give some insights into our gateway design and the protocol extensions that we evaluate and compare to vanilla ICN. I will show implementation details and our measurement deployment, which we use for the evaluation. And finally, we'll conclude and express future research directions. So what are the problems when connecting these networks in a delay-tolerant manner? In the remainder of this presentation, I will focus on NDN-style ICN. So, as we all know, interests are central in the receiver-driven control loop of ICN. They trigger data transmission in the first place, and in the second place, they trigger retransmissions in case no corresponding data has been received within a certain time. But the retransmission procedure is unspecified. Pending interests are a temporary forwarder state and implement the semantic forwarding property in ICN. This is to record the downstream phase that corresponding data has to be forwarded on. And the secondary function of PIDs is to enable interest aggregation, a feature that prevents multiple interests for the same data object to be forwarded on the same path. While interest aggregation means suppression for all but the first interest that has been forwarded in a certain time, that's the interest lifetime. When considering producers at the edge with untypical round-trip times, it seems straightforward that consumer applications provide certain knowledge about this time domain and trigger an interest retransmit at reasonably long time intervals. This requires PID state to expire timely. Otherwise, an interest retransmission would always be suppressed by on-path forwarders. But short-lived PID state conflicts with the long and varying producer delays introduced by the edge network. Data that faces a forwarder without pending interest will simply be rejected. So one could argue that the interest lifetime needs to be shorter than the retransmission timer. To cater to delay-prone networks, one could increase both values, the retransmission interval and lifetime. They would need to be adjusted for the end-to-end round-trip time. NDN interest packets provide an optional lifetime field that allows consumers to request more suitable interest lifetime durations. The default value is 4 seconds, which clearly is insufficient for our use case. While technically this seems like a solution, we argue that this is not likely to work well in real-world deployments. Why? First, high-speed forwarders are not likely to honor non-standard interest lifetime values. Second, in DTN scenarios, producer delays and thus consumer-defined interest lifetime values could be significantly higher than the 4 seconds. A core router might just object to spend more memory resources storing many interests for a very, very long time. And third, the round-trip time may change unpredictably, so the interest lifetime and consumer interest expiration time would have to be adapted constantly, which might introduce inefficiency. In practice, there are alternative retransmission techniques that we have considered in our work. In-network retransmissions, like the default case for CCN Lite, the ICN network stack, allows for long-lived bit state on forwarders without suffering from interest aggregation, since each forwarder triggers retransmissions autonomously. Now, the problem with that approach is that each on-path node needs to guess suitable timeout values instead of just the consumer application. Retransmission suppression, as implemented in NFD, suppresses same-name interest within an interval, which allows forwarding of retransmissions even in the presence of a matching PIT entry. The suppression interval still relies on the estimation of the round-trip time. The main purpose of this suppression mechanism is the prevention of DDoS by interest flooding, so fast sending rates, but dealing with very long and differing round-trip times still remains unsolved. To summarize this, guessing suitable timeout values for vastly different round-trip times is challenging. Furthermore, we cannot expect high-speed forwarders in the internet to honor non-standard and untypically long interest lifetime values. Instead, we argue for dealing with these round-trip times explicitly without interfering with the NDN interest lifetime. And this is why we included extended ICN protocol mechanisms to relieve forwarders from domain-specific knowledge. Now, in the following, I will introduce our LoRa gateway behavior and the two delay-tolerant ICN mechanisms that I have mentioned before. A gateway serves one wireless LoRa network and acts as an application-agnostic caching forwarder that connects the narrowband LoRa network to the internet. It follows regular ICN behavior in the upstream direction, and in the downstream direction, it leverages knowledge about the widest last hop and adjusts timeout values accordingly. We have added a node registration feature after a LoRa node joins the network. A node registers an individual name prefix at the gateway, which acts as a node custodian. LoRa nodes can only serve content under that name prefix. Data provisioning by IoT nodes commonly happens sporadically. Our gateway accepts unsolicited ICN data messages from registered LoRa nodes and acts as a LoRa data cache. Content objects are stored in the gateway content store, and it responds to interest messages from the internet. This approach relieves the wireless domain and minimizes energy consumption on the battery-driven LoRa node. Furthermore, the slot-based DSME MAC layer naturally assists prevention of DDoS attacks by unsolicited data message, while a malicious node can simply be muted by the gateway. So we include two delay-tolerant ICN protocols in our work. The first one is consumer-initiated. We call it delay-tolerant data retrieval. Thereby, an internet consumer can request content from LoRa nodes. We leverage the concept of remote method invocation for ICN, namely RISE, that supports longer data retrieval times. Upon reception of a so-called RISE request initiation interest, the gateway forwards the interest to the registered LoRa node. A so-called thunk response data packet contains an indication of the estimated waiting time, leveraging knowledge. The estimated data arrival time enables the consumer to set an appropriate retry timer without the need for specific producer knowledge. After repeated interest, the data item is likely served from the gateway cache. So the second protocol is producer-initiated. We call it reflexive push. Registered LoRa nodes place content in the gateway cache using the aforementioned data provisioning method. We leverage the phoning home use case of the reflexive forwarding extension that has been proposed to the ICE Energy for standardization. It defines two nested interest data exchanges. Content placement on the gateway triggers forwarding the data name to a node on the internet. The consumer returns a reflexive interest, retrieves the content from the gateway as usual, and finally, a data ACK terminates the initial interest. So in our evaluations, we compared these two protocols, reflexive push and delay-tolerant data retrieval, to vanilla ICN, and thereby we apply three different configurations to compare vanilla ICN. The first one is our baseline scenario with common parameter settings. Interests indicate a lifetime of 4 seconds, and retransmissions happen after 1 second, reflecting the initial round-trip time estimation of TCP. In the second case, a consumer that is aware of the long time domain indicates an interest lifetime of 60 seconds and sends retransmissions after 15 seconds. High-speed forwarders, however, do not adopt this long interest lifetime. The third case uses the same parameters as vanilla 2, but this time forwarders do honor the long interest lifetime. In all three scenarios, we will also compare the case for consumer retransmissions and in-network retransmissions. But first, let's have a look at our implementation and deployment details that we utilize for the evaluation. We deploy our long-range sensor application on common low-power IoT hardware. In more detail, the NRF microcontroller consists of an ARM Cortex-M4 processor and provides 256 kilobyte of RAM, 1 megabyte of flash, and runs at 64 megahertz. The LoRa radio is an external Semtech SX1276. Our sensor node is operated by Riot and our network stack, which is visualized on the bottom right of the slide. On top of LoRaWi, the DSME LoRa adaptation layer and OpenDSME, an open access MAC implementation, handle media access and operate the sensor node as a reduced function device, which synchronizes to the DSME slot frame structure indicated by a coordinator. ICN DSME is a simple mapping of ICN packets onto DSME. And finally, on top of the Riot network interface, we use CCN Lite as a network stack and integrate protocol extensions in there. To reduce implementation overhead, we deploy our gateway on the same hardware as the sensor application, although in practice, these gateways are not constrained in memory or energy. Our gateway acts as a coordinator for wireless nodes, and it operates a second Ethernet-based interface, which connects to a common Linux-based workstation that bridges to a virtual tap bridge. Now, the fast internet is emulated by Riot native instances, which allows to execute the same code in a Linux process. Thereby, we emulate two internet nodes in Mininet, one forwarder and a consumer. Both links expose a latency of 20 milliseconds, and we vary the link loss between 0 and 5%. So now that I have introduced our measurement setup, let's look at the evaluation of the system. In our measurement application, we use unique content names. Data contains either a random integer value or an ACK, NACK, or wait instruction. Every content item is transferred once with an average interval of 1 minute. We evaluate the completion time of successful transactions. These values are mainly affected by the superframe structure of DSME, which dictates the maximum latency of approximately 30 seconds in this MAC configuration. Data losses result in infinite completion times, so the end value of each of these graphs inherently reflects the success ratio. We first look at the baseline case, vanilla 1. Less than 20% of requests are successful and finish within the default PID time of 4 seconds. This is the case for interests that luckily arrive at the gateway just shortly before the transmission slot of the MAC occurs. Consumer versus in-network retransmissions and link loss show almost no effect because the prevalent obstacle here is rejection of data. In a nutshell, expired PID state prevents long round-trip times, and future retransmissions at an inappropriate timescale introduce overheads without improving reliability. Vanilla 2 is the case for a delay-aware consumer. Steps at 15 seconds indicate the retransmission interval of the consumer, and as indicated earlier, this requires on-path PID state to expire fast, avoiding interest suppression. All transactions finish in less than 45 seconds, regardless of link loss. In short, application-aware consumers can recover losses, but the performance directly depends on the arbitrary poll interval that we have actually set to 15 seconds in our case. So this approach is still highly susceptible to varying delays. In Vanilla 3, forwarders do adopt a long interest lifetime to set their PID timer. Cases without link loss require 32 seconds at max to retrieve all content, which directly reflects the delay distribution of the MAC. The long PID state on both consumer and forwarder allow data forwarding whenever it's ready. But the case with link loss demonstrates the drawback of this approach. Long-lived PID state on the forwarder prevents effective loss recovery by consumer retransmissions and drops the delivery rate to 80%. In-network retransmissions recover some losses and result in 94% delivery. Now, the problem with this approach is that we cannot expect forwarders to adopt arbitrary PID timeout values. Long PID state prevents consumer-based interest retransmissions and is unreliable in lossy environments. In-network retransmissions can improve the situation, but require forwarder knowledge of the latencies, a requirement that we want to exclude in our design. In the delay-tolerant retrieval case, requests finish in almost exactly 32 seconds, which is a returned wait time of the gateway after the first interest request. With losses in place, two effects are notable. First, 5% of the requests finish in less than 3 seconds. Here, a loss of the first data packet, which contains a wait instruction, has triggered an in-network retransmission that could already be satisfied by the gateway. Second, 8% of the requests are not satisfied at all, which is actually a simple implementation side effect. More details can be found in our paper. The consumer-initiated delay tolerant retrieval overcomes requirements for long pit state and stops blind polling, and further renders consumer or forwarder round-trip time estimation is unnecessary and leaves this to the link-aware gateway. With the producer-initiated reflexive push mechanism, transactions finish with 100% success, and the completion times reflect the delay distribution of the MAC similarly to Vanilla 3. The additional round-trip time of the nested double interest data flow has a negligible overhead when directed towards the fast network. Losses are smoothly recovered by in-network retransmissions at minimal time overhead. Contrasting Vanilla 3, this approach works with arbitrary producer delays, and it forgoes the need to adopt long interest lifetime values on internet nodes. Summarizing, the reverse transaction flow in reflexive push reflects IoT data generation most naturally. This protocol facilitates reliable and timely transactions and operates most efficiently, providing the best energy saving capabilities among all alternatives. We have performed different kinds of evaluations, but please go. More evaluations that we have performed, you can find in our paper. So now let's come to the conclusion of this presentation. In this work, we have observed that interconnecting networks with vastly different round-trip times is challenging. We found that ICN has the unique potential to enable robust communication to LoRa nodes in challenged edge networks without requiring application layer relays. And we have contributed a complete OS-level implementation of ICN DSME LoRa and two ICN style extensions together with a reproducible evaluation environment. Our results show that the two protocol mechanisms for internet consumer-initiated and LoRa producer-initiated communication exhibit high reliability. Compared to vanilla ICN, they enable targeted completion time and overcome polling. ICN DSME LoRa provides low power consumption and enables IoT node lifetimes of over 1 year when operated from an AA battery. The list of future work is long. In future work, we will integrate an estimator model in the gateway. The gateway thereby can leverage link knowledge to reduce the round-trip time in our delay-tolerant retrieval case without any application awareness. We will explore security aspects, which will include the bootstrapping of LoRa nodes and gateways, a secure registration process, which requires trust to the gateway, and authentication of LoRa nodes before the gateway acts on its behalf. We will evaluate more complex topologies, including multi-gateway scenarios, as well as node-to-node scenarios, and finally investigate additional use cases like remote method invocation and firmware updates on IoT nodes. Thanks for your attention. Our code is reproducible under this URL. You can also find this video recorded on this GitHub URL. And yeah, thanks again for your attention.
Thank you for the interesting talk. Any questions from the audience? Okay. Let's.
I'm available and it's like the whole rest of the day and morning for you. So.
I don't know. Will he be able to hear me?
I think it sounds better than before. Yeah.
Okay, so I'll try to speak very loud, or very microphone. So one thing I'm a little bit confused is what exactly, I mean, the proposal is. Well, the last one, last approaches is basically changing the communication model to some kind of a push thing, which I mean, the reason I'm mentioning is because it simply changes how communication is working. So, for example, if there is an interest, then whoever's requested data is responsible to fetch that data eventually. If we're talking about data being pushed from the LoRa device, then if there's a loss, nobody knows about the data. So it's kind of, yes, it may solve some of the delay problems, but I'm not 100% sure it's not breaking other things. And so I don't think that was part of the paper and part of my confusion. So maybe the question is, what is the suggestion?
So the push is one of the. I mean, basically that's like a framework that has different features. It has the producer initiated and consumer initiated sides. On the producer initiated side, this unsolicited data push terminates at the gateway. So, and this is to optimize. I mean, to deal with the latencies and optimize energy consumption on the IoT side of things. And basically, this enables the node to place its content in the gateway cache. And from there on, well, you have two options. The first option is follow the reflexive push mechanism that we have implemented as a proof of concept here and evaluated. And the second one is I would say the usual one, how to synchronize data sets. But this is not part of this work.
But still, like you saying, the producer initiated publishing in a cache. But if there is a loss, how does the producer will know if anything actually reached the gateway? There is no confirmation.
So, okay, yeah. Well, this is
Pushing data, so there's
okay.
no interest. So
This is the last.
that's after. So I mean,
to make sure that the data gets to the gateway.
no. So reflexive forwarding from the presentation was from the gateway.
Yes.
I can show the. Okay.
Well, yeah, I can try to share it again. Do I sharing?
I mean, no worries. I'll reread the paper then.
So it's a bit hard for me to follow here. Is this answer?
Thank you. Is someone has other questions? Okay, let's move to the next paper. The ICAS dynamic information synthetic cross-layer multipass for one speech network. Okay, the video will be presented.
Hello everyone, this is Tianlong Li, a PhD student in computer science at Beijing Institute of Technology. Today I'm presenting our paper ICAST, Dynamic Information-Centric Cross-Layer Multicast for Wireless Edge Network. So NDN naturally supports multicast with its pool model data plane. Instead of pre-configuration multicast groups in NDN, the interests with same name are merged in the PIT, and when the data retrieved, the network layer naturally multicasted to all the consumers based on the interfaces recorded in the PIT. Hence, NDN naturally supports dynamic and flexible multicast. Multicast has the potential to serve content delivery requirements, especially for the wireless edge network in which nodes are connected via shared media, and multicast can reduce the network traffic. However, the benefits of NDN native multicast is limited by the current link layer. For a long time, the internet is host-centric rather than information-centric, and the link layer design is also based on addresses. For example, there is destination MAC address field in the Ethernet frames and the receiver address field in the WLAN frames. We know that in NDN, data packets follow in reverse the path taken by the corresponding interests. In the link layer, transmitting data via unicast or broadcast is easy, but the NDN native multicast supporting cannot be taken for granted. As illustrated, the multicast requirement and the groups are formed dynamically in NDN, and the network layer supports native multicast. However, in the link layer, the unicast frame can use remote hardware MAC address for transmission, but the multicast frames, what destination MAC addresses should they use? Hence, there is a gap between NDN multicast and the host-centric link layer multicast. How to map a dynamic destination group to a MAC address and build information-centric multicast via address-based link layer. In traditional multicast methods like IGMP, the idea is using a specific MAC address to represent a preset group of members. This works for relatively static multicast. This works for the relatively static multicast requirements, but for the dynamic situations, such as same requests from user 1 and 2, then a group address needs to be configured. Same requests from user 1 and 3, another group address needs to be configured. Then maybe same requests from user 1, 3, and 4, and so on. Notice that in the traditional method, the whole 48 bits of MAC address is used to identify one specific group, which is inefficiency for dynamic multicast. The key idea of ICAST is using bit positions of MAC address to identify members and generate groups dynamically. For example, all users are allocated different bit positions. To multicast data to user 1, 2, and 4, just set their bit positions in the MAC address to 1 and the other bit positions keep 0. With this, ICAST uses 1 bit of the MAC address for one node in the local network and is able to dynamically merge members into groups on demand. ICAST has the one-time initialization phase and the normal communication phase. The initialization phase happens only when a new node joins the local network. In this phase, the access point allocates an unused bit position for it and notify the result to the node. For details of the MAC address redefinition, ICAST separates the MAC address into n bits fixed meta part and n bits dynamic allocation part. The meta part uses the least significant bit to identify that this is a group address, and meanwhile it distinguishes ICAST MAC addresses from other protocols. The n-bits dynamic allocation part is used to identify the end nodes in the local network. After allocation, the access point records the relationship with a lookup table named MAC mapping table. Note that the initialization phase does not configure any group. It just marks all end nodes with bit positions and let each end node knows the one allocated to it. The group forming happens in the communication phase. The communication phase consists of dynamic grouping and bit mask filtering. The former one is performed by the access point to send multicast frames, and the later one is performed by end nodes to correctly receive multicast frames. The dynamic grouping is triggered by retrieved data and is illustrated in the figure. Let me present this step by step. First, when the access point retrieves data and the corresponding bit entry has a set of phases, which means the data need to be forwarded via multicast. Then, the access point finds the bit positions of those end nodes from the MAC mapping table. After that, the access point just needs to execute bitwise OR operations with those bit position marked MAC addresses to generate the group MAC address. Note that in the n-bits dynamic allocation part of the generated MAC address, the bit positions of all intended end nodes are set to 1, while others are kept 0. Hence, the generated MAC address carries the information of all destination end nodes. Finally, the access point sends out the frame with that address via multicast. By the way, the dynamic grouping does not influence the normal unicast processing. So the access point can perform multicast easily with dynamic grouping. Then is how the end nodes receive the multicast frames. The end nodes use bit mask filtering to distinguish whether a multicast frame is intended for it. For example, of the user 1, in the link layer, it recognizes the data frames with name 1 and name 2 are ICAST multicast frames due to the value of the former n-bits fixed meta part of their destination MAC addresses. While the end nodes does not carry the whole MAC address represent for which group. It only cares if itself is included in the group represented by the destination MAC address. Hence, it only checks the value of its bit position in the destination MAC address. The value of that bit position in the data frame with name 1 is 1. So it passes the data to the network layer. The value of data frame with name 2 is 0. So it drops this frame and prevents from unnecessary packet receiving. For the data frame with name 3, the least significant bit in its destination MAC address identifies that it is a unicast address, so the network interface card processes it normally. So this is the processing of ICAST. The key idea is using MAC address as separated bit positions rather than a whole identification. Based on this, the access point can dynamically grouping different end nodes on demand, and the end nodes can correctly receive multicast frames with bit mask filtering. Well, in our paper, we also propose a hash-based variant. This variant is mainly for mobility scenarios. In the basic ICAST, the bit position allocation happens only once for each node. This is negligible for a relative static network. However, considering common cases for real edge, such as the Wi-Fi network in teaching building or malls, where people with laptops and phones come and go. In these real environments, nodes join and leave the network frequently, which may cause a high bit positions management overhead. Hence, we propose the hash-based ICAST. The hash-based ICAST roughly has the same communication phase as that of basic ICAST. The key of it is using hash calculation for bit position allocation. Instead of managing the mapping relationship with the MAC mapping table in hash-based ICAST, the access point only needs to publish the hash function it used for allocation in the initialization phase. Furthermore, we can preset default hash functions with specific MAC prefixes to further simplify it. The real allocating operation is delayed to the dynamic grouping. In basic ICAST, dynamic grouping needs to get the bit positions of all the destination end nodes via the MAC mapping table, while in hash-based ICAST, the access point hash all destination end nodes hardware MAC addresses to get their corresponding bit positions. The bit mask of each end node is also generated by hashing their own hardware MAC address. Hence, there is no extra overhead caused by end node dynamic connections in hash-based ICAST. We evaluate ICAST with a real testbed. We use an industrial personal computer as the access point router, 15 Raspberry Pi as end nodes. For comparison, we also implement an IGMP like the multicast method named the IIGMP. To be specific, when a new multicast group is established by the PID, IIGMP will allocate an unused 6 bytes multicast MAC address and broadcast a special data packet as the notification to the corresponding end nodes. After that, the data packet of the requested content will be sent out via multicast with the allocated MAC address. Each experiment is repeated 50 times, and we take the average values as the results. We also carry out two scenarios for evaluation. One is file transmission, and the other one is live video streaming. In the first scenario, we deploy a file download server on the provider side, a client on each of the 15 consumer end nodes. In the experiment, N end nodes run the client at the same time to request a same file. We measure the network traffic overhead and the forwarding operational cost. The results are shown in the figure. As the Valenia NDN use unicast in the link layer, its traffic overhead grows linearly with the number of requests increasing. In contrast, the traffic overhead of both ICAS and IIGMP grows slowly. ICAS reduces up to 73% of the traffic at the edge compared with the vanilla NDN. It's worth to note that the traffic overhead of all multicast methods increased quickly after 10 nodes. To explain this, we further measured the proportion of unicast and multicast. From this, we can see that with end node number increasing, the multicast traffic proportion of all methods are roughly static. Most of the extra traffic are unicast traffic. The unicast traffic in ICAS and IIGMP are triggered by either retransmission for the packet loss or the desynchronized interests. Last but not the least, this figure also shows that there are more multicast traffic in IIGMP than that in ICAST. This is because in IIGMP, when a new multicast group is established, a notification data packet has to be sent out, whereas in ICAST, such packets for management protocol are needed only once at the moment of new end nodes joining the network. Hence, ICAST has less overhead in terms of management traffic. In the evaluation, the processing delay is measured from the time of the access point retrieving a data packet to that of the access point putting it into the transmitting queue of the network interface card. As shown in this figure, ICAS reduces 58% of the forwarding processing delay in average compared with vanilla NDN. In vanilla NDN, the access point has to copy and send out data packets multiple times via unicast. IIGMP takes more operational cost than ICAS as the AP has to look up its group record table and send out an extra new group notification packet for each time of new group establishing. Thus, IIGMP takes 1.2 times average processing delay over basic ICAST. In the second scenario, we deploy a live video server on the provider side. We modified the network socket part of mPlayer to enable the live video playing over NDN packets. In this scenario, the live video on server lasts for 60 seconds. N and nodes request the same live video streaming, but start requesting at different time. We measured the network traffic overhead and the traffic reduction ratio. The results shows that ICAS has the minimum traffic overhead. There are two shortcomings of the conventional group management method. First, upon the dynamic request aggregating and groups establishing, IIGMP causes a lot of extra notification packets, and meanwhile, the growth of group management table takes more overhead. Second, the notification packets are sent out via broadcasts, which also face the possibility of packet loss. If the first notification packet fails to be received by a group member, this member cannot receive any data sent to this group until the AP rebroadcasts the notification. However, groups in NDN are highly dynamic, which means the lifetime of an individual group is probably short. Hence, IIGMP suffers from lots of useless work upon the dynamically requesting and grouping, and consequently becomes inefficiency for wireless edge NDN. In contrast, ICAST facilitates the establishment and management of dynamic groups. The traffic reduction ratio of ICAST achieves 1.4 times over that of IGMP. So the evaluation results shows that although the current wireless network is lack of link layer error recovery supporting for multicast, ICAST can still reduce over half of the network traffic in case of 3 to 12 clients requesting the same content. Besides, ICAST has the least operational cost and performs better than traditional IGMP-like methods when faces dynamic requests. such as the live video scenario. Besides, we further measure the packet loss rate in the first scenario. We can see that with over 10 same requests to end node, the traffic overhead is dominated by the growing packet loss rate. This explains why the unicast proportion of both ICAS and IIGMP grow fast. Link layer error recovery supporting is beyond the scope of this paper, but that is a subject for the future work. In our future work, the most important is reducing the multicast packet loss rate. In this paper, we design ICAS with minimal link layer modification. The only fundamental link layer modification is redefining the usage of the destination MAC address. Hence, ICAS is orthogonal with previous studies, which focus on multicast error recovery and rate adaptation, and we believe that it is promising to cascade ICAS with them to mitigate packet loss rate and achieve high performance. For the second, as ICAS can have warranties for adapting with different scenarios and the fixed meta part in multicast MAC address can be used to identify their types. Hence, exploring more scenarios and the corresponding ICAS warranties, and finally forming specific dynamic information-centric multicast protocols is good for future researching. Last but not the least, our present work implements ICAS in software, yet the design of bit mask filtering is promising to be implemented in hardware, which has the potential of further reducing the CPU usage and improving the energy efficiency for end nodes. We hope that ICAS can finally be developed as a series of efficient and practical dynamic information-centric multicast methods with specific protocols. For the summary, our work contains both intellectual and practical contributions. On the intellectual side, we propose an efficient way to dynamically form groups and filtering frames under the current link layer scheme. On the practical side, our implementation indicates a promising opportunity for deploying NDN with ICAS at edge networks to reduce the traffic overhead and the forwarding operational cost. ICAS bridges the gap between NDN multicast and the host-centric link layer multicast, and we believe that ICAS can finally unleash the potential of information-centric multicast in various edge networks. Thank you for your listening.
If the last operation is also online. Okay. Any questions from the audience? Question.
Hi, thank you. Not sure why the, your curve of your overhead, one of the first graphs you showed, looked sort of nonlinear for IGMP and IGMP hash, and it looked like it would cross the linear curve of vanilla NDN if you went out beyond 15 or whatever it was. And I wondered, first of all, I didn't quite understand why it was nonlinear, but would it actually cross if you had, 25 clients?
Well, actually, this is due to the packet loss. In the various in the W line, there is no error coverage mechanism, and in this paper, we mainly solve the problem of how to map a dynamic destination group to a MAC address and to enable dynamic multicast. Hence, the error coverage and is future work. It's a future work, and in this paper we does not and in this paper the packet loss was going on, so the overhead was grow quickly after 10 nodes.
Okay, so it was an artifact of the 802.11 link layer protocol. So what version of 802.11 was it? Could you say what version of 802 it was you used for the evaluation?
Could you speak again?
That's okay. I'll look in the paper. Thank you.
Any other question from my side? There is one question from Sam. From Doug. Doug has asked, nice work. This is not limited to why still needed. You could probably also get it from the ICN data sharing between data centers. In the slide, you can see the question. Could you answer?
Yes, it's a good suggestion for our future work. This is not limited to the wireless network, but we think it can benefit well in the wireless network, because in the wireless network, when you send data out, all the end nodes was connected with the shared media. So if you use the unicast, there is a waste. But actually in the Ethernet network, yes, this can be used, but in the Ethernet network, when the data was sent out from different ports, in the driver of the network interface card, the data may be copied still may be copied multiple times. Hence, in our paper, the scenario is chosen as a wireless network. But yes, it is not limited to wireless network.
Okay, thank you. No question from the audience. Okay, this is the last presentation of this session. Let's thank all the presenters. I would like to close this session and hand over to the General Chair, Dr. Asada, for the